Okay, great. So for esters, what do we need to do? So let's see some examples, right? So if you want to show the example of an ester, so this R group will be typically like for, again, our kind of starting level, this will be some sort of alkyl group. So maybe you'll have like a CH3, right? So attached to the carbonyl NOH. So this is going to be an example of like a very simple carboxylic acid. Why is it like simple? Because it's kind of like literally mundane, right? You can encounter it every day in your kitchen, right? So it could be like in vinegar, for example. So that's what you have, right? So the solution of vinegar contains like about 95% water by mass, right? And then 5% of this, right? So this is going to be the carboxylic acid. It's called acetic acid, right? So in other words, so that's going to be acetic acid. So it's like a pretty popular compound, right? So, and then of course we can have like more complicated acids. So which can be, for example, we have instead of methyl, we can have like a phenyl, right? Or maybe some kind of like a pentyl group. So that could be, again, like many variations. So that's acetic acid. So if you want to look at the example of an ester, so here you go, right? It is, as I said, a derivative of the acetic acid. So it is derived from it. So you can do something like this, right? And instead of H, we'll have the R, right? So let's do that. So R could be like any alkyl chain for now. So maybe it's going to be, for example, like CH2 and CH3, right? So this one is like a very, again, popular ester at this point. So this particular formula, so because it's used a lot as an organic solvent in organic chemistry, right? In synthesis. So it could be also used in some kind of like cosmetic applications, for example. So in like perfumes, could be found in some kind of like wines to some extent. So yeah, but this is an ester, right? And then you have like one major switch from this H to now this group, right? And then if you think about it, so you'll still have the single bond between O and H, and here you have still the single bond between oxygen and carbon, right? So just to fulfill the 4 valences of this CH2 carbon right there. So that's an ester example. So now let's move on to the next slide, right? So like what do we have? So some examples of the acids, right? So it's going to be pretty much the most simple carboxylic acid. It is going to be the formic acid, which can be found in ants, right? And then the formula, if you want to show that, so we can write it out. It's going to be something like that, right? So this is the formic acid example. So here we go, right? So you have the hydrogen attached to the carbon, and it's going to be this example of the carboxylic acid with just one carbon, right? So that's pretty much the one and only example of the single carbon carboxylic acid. Okay, so now let's take a look at the naming, right? So here are the rules, right? So they're kind of like listed in this boring fashion, but it's mostly for you to review that on your own, right? So and then from here we can take away that the acids in the name will have the OIC or oic, what's the suffix, right, in the name. So now let's take a look at some things, right? So the carboxyl carbon is always number 1, right? So then if you look at the acid structure, you cannot put this carboxylic acid somewhere in the middle as a ketone, right? So ketone can be like in the middle of the molecule, kind of closer to the end and such. Aldehyde, for example, as you recall, can be only like on the edge, right? On the terminal carbon of some sort of like a huge chain in like organic molecule, right? Same is true about the acid. You cannot attach anything to here, right? To this hydrogen, for example. Hence, you cannot put your carboxylic acid group like in the middle, right? So you can do it with esters though, so that's fine. You can see here, it's kind of surrounded by the carbons, right? But about this a little bit later. So, but for the carboxylic acids, so you will have some sort of like chain like this, right? You cannot put the carboxylic acid like here somehow, right? So it will be only like hanging out from the terminal carbon like this, right? So, or if you want to attach somehow the carboxylic acid here, so the best you can do, you cannot turn like this, for example, carbon into the carbonyl carbon. If you do that, then that's it. You stop here, right? So you make a ketone, right? So if you want to somehow make an like acid here, then yes, you can do that, but you will need to have like a bond carbon, right? And then as you can see, so the here, so what's going to happen is that you are going to have the branching, right? So you're going to have the branching of this carbon, and then that's going to be like a way to show that. But you cannot like put your carboxylic acid like inside the chain. In the best case scenario, it will be like on the side of the chain, right? So, but typically, it's like what we do is that like anyway, so the carbonyl carbon of the carboxylic acid will be always numbered as number 1. Right, so then we are going to, of course, determine the longest chain in the molecule, and then we are going to include all the carbons in the count, right? So just like that. So like we need to count however many carbons we have in our longest chain, including the carbonyl carbon, right? So same was true about like aldehydes, for example. So here you can see some examples already of acids, right? So this one will be kind of just 1 carbon. So here, if you want to count the carbons in this like acetic acid example, so we can do that. We are going to circle and count the carbons in the circled area, right? So 1 carbon, 2 carbons in the acetic acid, and then here we have like a lot more, like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So as you can see, we can already have like a lot of examples, right? So if we look at this like semi-botched structure, we are going to find the longest chain. And then, yeah, that's pretty much going to be a little bit more difficult example, but we can still make it by counting the carbons. 1, 2, 3, 4. Not so long, right? So 1, 2, 3, 4, 5. So that seems to be kind of the longest chain to me. So 5 carbons, right? So that's pretty good. So that's going to be our longest chain, and you can see so that here still the longest chain, this kind of like carboxylic acid functional group is on the like edge, right? It's not somewhere like in the middle of the chain. So but anyway, so here we go. So we found like the longest chain here, so we can start numbering the carbons, right? So like when you can use this example right away, 1, 2, 3, 4, 5, right? So it's going to be like 5 carbons in our carboxylic acid. So now let's maybe actually take a look at this example and then transfer it to like the better sheet and see how we can name it, right? So here we go, some kind of like naming conventions, right? So carbonyl carbon will be number 1. So we used to have something like that. So we had carbonyl carbons. So I'm going to show it in a little bit like inverted fashion. So then we had 5 carbons, 1, 2, 3, 4, 5, right? And then we used to have also ethyl attached to carbon number 2. So it was like that. Okay, so substituted acid already. So we count our carbons. So this is going to be starting with number 1, 2, 3, 4, 5. Longest chain done, right? So then we're going to have our suffix will be OIC, oic, right? And then if you see this functional group, right? So if you know that this is going to be the carboxylic acid functional group, then you will have the name acid, right? Inside the name of this compound, right? So now if we have like 5 carbons in the longest chain, we need to think about alkanes. And then we need to recall the root, right, for the parent alkane. So 5 means, is it like hexane? No, it's 6, right? Butane, it's 4. Now it's going to be pentane finally. So pentane. So pentane is going to be the parent alkane. So, but for our intents and purposes, we are going to modify this name a little bit more. Pentane, right? So that's what you will get from the parent alkane name. Pentane, and then you will kind of connect it with this, right? So pentanoic acid. So, but not so fast because you have, so it would be good, it would be pentanoic acid without this guy, right? Without ethyl. So right now it is just pentanoic acid, right? Like this. So, but if you have the ethyl, So you need to like show where the ethyl is at, right? So let's maybe like circle that in red. So that's going to be our one and only substituent. So apparently it is on carbon number 2. So this seems familiar. On carbon number 2, there is ethyl. So let's just show it this way. 2-ethyl pentanoic acid, right? So that's going to be overall our kind of result of this naming. So here you have some kind of simpler examples, maybe a little bit. So this is 1, 2, 3, 4, 5, and 6. 6 carbons in this chain will result in hexanoic acid, right? So that's going to be hexanoic acid. So then you have, again, the longest chain, which we can identify 1, 2, 3, 4, 1, 2, 3, 4. No matter what we go, right? So how we go, we still get the longest chain of 4 carbons. So this will be from butane, consequently, butane derivative, right? Butanoic acid, but also on carbon number 3, starting with this as carbon number 1, we're going to have the methyl, right? So that's the methyl right there. So 3-methyl butanoic acid will be your kind of like result in this naming. Okay, so that's quite nice. So now some kind of like general like knowledge, right? So where this can be found, right? So why we need to care about the acids. So looks like they can be found in some products, right? So such as in the fat. So in the fat, there is like 47% palmitic acid, apparently, maybe in the beef fat, according to the picture, right? So, and you can have, like, as you can see here, like various structures for your carboxylic acids. So such as like maybe like huge chain of carbons, right? So we have here at least 14 carbons or 14 CH2 pieces alongside the other things such as methyl and carboxyl itself, right? So that's one example. So then we can also have some kind of like more various structures such as like aromatic acids, right? So this one is the benzoic acid. That's kind of the first example of the aromatic acid, basically. So if you look at this, so like remember this question in exam 1, so like about how you need to like disconnect atoms and then attach something else, right? So here, if you look at the example of the benzoic acid, basically you started with what's it called? You started with benzene, right? So it used to be like this. So that is the benzene molecule, and then we can show explicitly 1H, right? So then if you go ahead somehow, like chemically, right, of course, like break this H bond, and then for now, you can just like switch it, right? So to something else, you would switch it to a carboxyl group, right? So now you will have your COOH right here. And now, so that's going to be all of a sudden benzoic acid, right? So it's like a very popular compound. It can be found as a preservative in juice, right? So, and yeah, whilst it preserves the like juice and soda, it is unfortunately a carcinogen, right? So if you see some sort of like benzoates, right, then be careful. So like from the medical perspective, I guess it could be like good for medical professionals and then like people in general, right? So like, with their health stuff and such. So basically the salt, right, of this acid, speaking of salts and then activities from the worksheet, will be like this, right? So this is going to be like a potassium. So potassium benzoate. So that's what it's called, right? So we'll talk about the convention a little bit later. So, but this can be used as a preservative, right? So, and this is going to be already the example of the salt of the like specific carboxylic acid. So you can find it like a lot of like food labels, right? But be aware it is a carcinogen, and it's unfortunately found in, for example, like Jarritos, right? So some of the Jarritos don't contain any sodium or like benzoates in general. Some of them do, right? So just be aware. So yeah, this is just a segue to like real life applications, so to speak. And now we have what? Like we have like more naming, perhaps, and then we can also switch to the ionization activity, right? So let's see. So like, what do we start with? So yeah, we have activity number 1. Let's take a look at this like before we start naming things. So like we have like 2 minutes maybe. So like demonstrate the ionization of a carboxylic acid with 6 carbons, right? So like we have that right now. So you can go ahead and do that. All right. So 6 carbons, right? So now it's going to be up to you to show some sort of acid, right, with a 6 carbon and its dissociation. So here are various colors for you, and then let's see what happens, right? So according to your peer, Olivia, so is going to draw something for us. Okay, so like we have like a good looking formula there. So like with all the things shown, right? So according to one of the undergraduate TAs who was here, Jane, right? So he is still around. He said, write out all your bonds which you are going to break, right? Especially which dissociate and participate in the chemical reaction. So it's going to be helpful. So in particular, we need to show this like OH bond. Yeah, that's a good adjustment. So, and then you need to pay attention to that, right? So, like Olivia is showing this for a reason. So, to draw your attention to the fact that it's like OH bond will dissociate, right? And then it will make us the respective products. So, that's going to be our goal right there. Maybe like center the piece of paper so that people can see what's happening. Okay, great. And then, yeah, that's well done. So awesome. So yeah, so you have all the stuff kind of like achieved. So that's well done. And now you see, so as I was saying, so just like we saw this example of actually it was acetic acid in the past, right? So we showed dissociation for it. And then I said, if you can get that part right, you will do it with any carboxylic acid of your choice, right? So that's going to be the one, okay? Like, well done. So then one thing, when you show those like hydrogens, right? So it's just kind of like the matter of positioning them. So it's all good, right? It's all like tetravalent carbons. Awesome, right? So, but when you draw something like that, so which you do a lot, I noticed show the hydrogens like that, right? So you see now it looks more like a tetrahedral shape. So, and kind of like more spread out, so to speak, right? So that's what we want to show. This is also looking like a tetrahedral, so like don't get me wrong, but it's like more kind of jammed, right? It's a bond, 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 but here it's like more spread out, just like something to keep in mind, right? And then here you have your H's. So they go like up or they go down, right? So as another instructor of mine was saying in a different language. So, but yeah, so that's what it would be, right? And you have some kind of like stuff here, maybe like your like famous carboxylic acid functional group, right? So then maybe in some sort of like R group, whatever it might be. So yeah, that's just kind of like the matter of drawing. So if you draw next time, just try to do it this way, right? So and then it will be like more Gen Chem conforming, right? So because you want to have the repulsion of those pairs of electrons from one another, and then they have to be spread out in the best possible fashion. Okay, so great. So now let's see. So we are going to take a look at typically for our kind of like exam purposes, we'll be looking at the like straight chain, more or less, carboxylic acid with the carboxyl function group. And then maybe some substituents in the chain as well, right? So let's maybe take a look at example A here. So see what happens. So I think I lost something. Okay, good. So found it. So like here, so like what we need to do, for example, A is of course find the longest chain, so like which we can do, and we will number it, right? So we'll start, this one will be number 1, right? So the atom, the carbonyl of the carboxylic acid will have to be number 1, right? So we can name it as such. So now we can count, and then we go like 1, 2, 3, 4, 5, 6, 7, 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So looks like it's like 8 carbons anyway, right? So there are potentially like 2 longest chains. So now let's see. Okay, let's count again. So like 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I found the chain, right? So which contains 8 carbons. So it's going to be like this one, right? As well as this one. 1, 2, 3, 4, 5, 6, 7, 8. So we also have 8 carbons. So, but now the problem is that, so we need to think about like which one wins, right? So if you recall, exam number 1, so there was this question, which basically, in which case we had like several competing chains, but the one which was more branched would win, right? As in, it needs to have like more substituents. So it looks like if we count this as the longest chain, 1, 2, 3, 4, 5, 6, 7, and 8, right? So this is methyl. And so there's a methyl here, a methyl there. So no matter which way you go, you will end up with the same kind of like 8 carbon chain, right? So this is methyl, so they're equivalent. So doesn't matter where we end our count. So, but the point is that we are going to have couple substituents, right? So, and then if we look at the chain, which I'm going to kind of show with a what's it called, laser pointer, like this one, 1, 2, 3, 6, 7, 8. So this chain, that straight chain parallel, like straight line, will contain only 1 substituent, right? So we need to look for the like more branched chain. So which is why this kind of crooked chain wins, because it has more substituents, methyl and ethyl, as opposed to isopropyl, right? If we just look at the straight chain with the isopropyl, and you need to be able to see the isopropyl here, right? So anyway, so we have our substituents, right? So we have 8 carbons, right? So like, what do we do with the 8 carbons? So it's gonna be the root, right, from the respective alkane, which will be what we have hexane, heptane, octane, right? So we have octane, so as our root, right? So octane. All right, so this is kind of like letting me down once again. So I'm gonna just be writing the name on this like a white piece of paper here. So octane, right? So then we are gonna use only this part from the respective alkane, and then we'll add oic acid, right? So if you have that, so you already have at least some partial credit, right? So that's a good news, right? Longest chain, like the root of the alkane, add the oic suffix, like that, right? And then you are all kind of like you are a little bit set, right? So now we have your octanoic acid, and then it's kind of double substituted, right? So we have ethyl and methyl. So we need to arrange them alphabetically. So EM, so we'll have ethyl first, then it's going to be ethyl. So ethyl, then methyl, right? So ethyl, then methyl. So that's how they will go. So now we need to like see on what carbons they are, right? So apparently on carbon number 7, we have methyl. So it's going to be 7 methyl. On carbon number 6, we have ethyl. So 6 ethyl. 6 dash ethyl. Then we have dash 7 dash methyl, octanoic acid. So I think it's going to be like that. So that's connected, right? So 6 ethyl, 7 methyl, octanoic acid. So this is going to be compound A. So then we'll have, so here I can just maybe like number things. This is going to be a little bit less complicated. So, but still 1, 2, 3, 4, right? So this is going to be a substituted butanoic acid, right? So because we have 4 carbons in the main chain and not so many options, right? Honestly, we have the Br, which stands for bromo. So basically, you saw Br substitute many times. So this is going to be called as 3-bromo butanoic acid, right? So 3-bromo butanoic acid. So then here we need to recognize the compound, right, by its common name here in part C, right? So this one will be the benzoic acid, right? So like we have for part C. So now let's move on to part C. So like we here have nothing more than benzoic acid with the substituent, right? So if you cover it, so here you should be able to recognize the benzoic acid. But of course, so like from, again, our perspective of exam 1, you somehow like remove this H hypothetically from just benzoic acid and you switch the hydrogen to the ethyl, right? So that's how you get the substituted benzoic acid. It would be nice if it were that easy, but it's not that easy, right? So there are ways, but we don't need to think about them right now. So, but now let's name it, right? So here we go. So we can use basically like 2 approaches. So we can see that again, so carbon number 1, right, as you remember from the aromatic stuff, so and then common names. So carbon number 1 will be here, right? In this situation, it's going to be a little bit of the exception, right? When you think about the common names of certain aromatic compounds. And there we agreed that whatever the substituent is attached, right, to your common named compound, this carbon will be number 1 in the aromatic ring, right? So it's like, not this is number 1, but this is number 1. So that's kind of like the exception here. But it's an aromatic compound, so their rules are different, right? So then we can name the number the carbons, right? So like we can go this way, maybe like counterclockwise or clockwise, right? So if we go counterclockwise, we're gonna go like 1, 2, 3, 4, 5, right? So that's gonna be high number relatively. If we go clockwise, we can also do that. 1, 2. Sorry, where's the laser pointer? Okay, we'll go 1, 2, 3. So 3 is much lower, right? So you can just say that on carbon number 3, there is an ethyl, right? So and then this will turn into 3 ethyl, benzoic acid, right? So again, there is a common name for this acid, right? So like when you have this combination of atoms such as that, right? So this is going to be our benzoic acid. Remember, we had like toluene is a common name compound. Then we had like aniline and phenol, right? So that's pretty much it. So this one is called benzoic acid, right? Once again, benzoic acid. And then, as we know as well, so it is carcinogenic, right? So especially the salts, right, that can be like water soluble. These are like carcinogens that are derived from the benzoic acid. So that's benzoic acid. And then we can also see that actually we have the what's that? We have the substituent not on the next carbon, but like skipping 1 carbon, right? So this is going to be the meta arrangement. So we can also call it like M. So there's cursive M, meta ethyl, right? Meta ethyl benzoic acid. So that's another option. So yeah, that's like it, right? So that's where we are. So we look at the straight chain carboxylic acid with some substituents and then also benzoic acid. So that's going to be our like complication here. All right, so now let's see what we have next. So maybe it's going to be a good time for a review a little bit, right? Actually, we did have it, as a matter of fact, in maybe our 3rd exam, right? So we have the primary alcohol with an aromatic ring, and then it needs to lead to a carboxylic acid, right? So then your bonus question will be, you will need to make a salt, right? And then you need to make a salt from this carboxylic acid. So let's see if we can like recall it, right? So it's going to be a little bit of the review question, right? But this will tie in with the topic of today because it's going to be about the synthesis of the carboxylic acid. Typically, we need to think about, okay, how do we make such compounds, right? And then we can think about their like reactions, right? So before we move on to esters, maybe it's going to be like a good time for this activity number 2. It's a little bit on the challenging side, but maybe you can recall something and give it a try. So that's like there. So, and then like the second part here will be you need to make a salt, right? So we had the salt examples just now, right? Maybe several minutes ago. Actually, the carcinogenic salt in this case it was. So, but here you go. So you need to start with the primary alcohol that contains also the aromatic ring, right? So conceivably, there is an aromatic ring, primary alcohol, and an alkyl chain, inevitably. So because you need to have the primary alcohol specifically, and then you can make the carboxylic acid. So there was like a reaction starts with an R, right? So that leads from the primary alcohols to carboxylic acids. So that's your review. So perhaps it's gonna be like needed for like the fourth exam anyways. So but maybe you can recall it earlier. So that's good. So let's see. That's on the table now, and yeah, you can give it a try if you want. So like we'll think about that for maybe 30 more seconds, and then if not, then we will move on. So, but you did see that in the past. So maybe even several times, right? So we went from the alcohol to aldehyde. Okay, so like we have the candidates. So let's see what we can make from that, right? So maybe we can even get all the parts done. So, but for now, synthesis of the carboxylic acids from the primary alcohol, and then make a salt, right? So that's going to do a little bit more latitude there.
Do I need a certain number of carbons?
It could be, yeah, it will be more than 7, yeah, because you have the aromatic ring, some alkyl chain, maybe 2 carbons in a chain, maybe 3, maybe 16. So yeah, that's your like prerogative here. But you must have the aromatic ring, so which contains at least 6 carbons, right? Carboxylic acid is at least 1 carbon from the carbonyl, right? So and then here you go. So that's like what you're going to have. Okay, great. So that's your primary alcohol. So like very good. So that's going to be actually called, what's it called? It's called a benzyl alcohol. So that's a very common compound. So we have a strong oxidizing agent. Great. So that's what we're going to have, right? So we need to have a strong oxidizing agent. And now actually you will make something already familiar at this point, right? So because this is going to be nothing more than benzoic acid. Great. So, and then if you want, you can make a salt from that. That's going to be the like second part.
Yeah, that was the part I didn't know. What was the?
So any inorganic base, such as maybe KOH, right? So, or sodium peroxide.
And would that be added onto the OH?
Yeah, that's right. That will be added to the acid, right? So, and we have the acid-base reaction, right? So it's the same stuff as from GenChem. The only difference is that you are going to have the carboxylic acid in action, right? So then you have a KOH, for example. All right, that's your inorganic base. So, okay, and now you have the acid-base reaction. Let's try to recall it. It's going to be ion exchange, right? So you have technically ion of H plus, ion of K plus, and then OH minus, and your huge anion from the carboxylic acid.
Is it a minus? And then it'd be
Yeah,
K?
that's right. It's going to be the minus there. So because, and then you have K plus. Great. So that's the one. And the byproduct will be, you can show HOH. HOH, so people need to figure out, right? So that this is water. All right, great, well done. So awesome. So that's your stuff, right? So here, literally, honestly, the new thing here. So again, if you show like that, either stick to the skeletal structure, right? So don't show any carbons, or this is going to be your like CH2OH, right? So this is all good, but show the H's here as well, right? So just don't leave it halfway. So eventually it will transpire maybe by the end of the semester, but yeah, it's okay. So it's all good, right? That's awesome done. I would say, and yeah, here we have it, right? So we will have the acid, right? So basically, yeah, that's oxidation with a strong oxidizing agent of the primary alcohol that leads to the acid. So like, well done. So this is a check mark here. So then we'll have the acid-base reaction, right? So like a quick review. So you'll have K plus and OH minus. And then technically, once this dissociates, it will make H plus, and then On the oxygen, you will still have the negative sign, right? So no matter what the acid is, so this stuff will prevail, right? So then you will have the so-called ion exchange, right? So because you are going to exchange the ions. So you used to have the plus minus combination. Now you need to make a new combination of plus minus, right? So I would say just kind of don't show this plus. It's not needed, right? So you will have this kind of like COO minus with the K. So that's how they will be connected, right? So that's going to be your salt. And then you will have technically H plus and OH minus. Together, they will make your HOH or H2O, in other words. So yeah, that's your like, typical exchange, right? So that happens. So we're going to look at those reactions more, of course, right? So maybe another thing, so you can even use it as a like a gift for yourself. So if you have something like that, let's say we're going to have the reaction between, let's say, like HCl and, for example, like KOH, right? So it's going to be exactly the same. Everything is the same as in what Lucas has just shown us, except this guy, right? Cl. So it's going to be also like a counter ion, but it's going to be not your like carboxylic acid derived anion, but it's going to be from this like inorganic acid. So then you have H plus, K plus, OH minus, right? So then they will react, and then what will they do, right? So they will make a new combination. You will have to have K plus associated with a different negative charge ion, which is going to be Cl minus. Okay, plus and minus will attract, right, by physics. And then you'll have HOH. So H plus and OH minus. So they will also associate, and then you will make something like that, right? So this is going to be your kind of like combination here of the ions. So you can grab this like after the presentation as a gift, put it on your like wall, as some people say, and then yeah, that's going to be potentially good for you, right? You'll be like Hamza. So yeah, so that's like what we are going to have here as far as like acid-base reactions are concerned, right? So, and then you will have the same principle with your organic acids as well. So now let's see. Okay, so now we're going to move on to the next nomenclature piece, which is going to be nomenclature of esters, right? Nomenclature of esters. So what do we have here? So basically, so esters look like that, right? So it's essentially the derivatives of the carboxylic acids when we switch the hydrogen from the OH to some sort of like alkyl chain. So here we just switched H to the methyl, right? We used to have, if you can think about it, right, we used to have the compound which would be like this, right? So if I cross out somehow this like thing, right? So, and then switch it to the hydrogen, I'm going to have the propanoic acid, right? So propanoic acid originally, but now we are going to deal with the methyl instead of H, right? So in the previously, what was previously an OH group in the carboxylic acid. So the suffix here will be 8, right? So, and now we can think about this as an maybe like alcohol part. Some people can like think about this way, right? So because here, if you look at this, methyl with oxygen, it's almost like an alcohol, right? So then also we have the acid part. It's going to be your like stuff, like tail with the carbonyl. That's an acid part. Why do we think about this way? Because we will look at the reactions of how to make actually esters, and officially they are produced from the acid and alcohol reaction, right? So that's why it's going to be a good idea to think about those parts right away. So before it's not too much pressure, right? So then how do we name it? So like naming it, so we'll still be about looking at the acid in which the H in the OH was switched to the alkyl chain, right? So here you go. So I'm going to use now the green colors or maybe just like a different piece of paper here, right? So, and see where we are. So yeah, basically, so it's called now methyl propanoate. Why is that so? It is so because you have your propanoic acid, right? So which is going to be CH3, CH2, carbonyl, like that, right? So this guy here. So let's imagine that we have like H here, right? I'm just gonna like say there is an H, right? So if you envision this in your mind's eye, then you can say, well, 3 carbons, right? So this is gonna be carbon number 1, whatever. So this is gonna be a propanoic acid because 3 carbons correspond to the propane as our base, like parent molecule, right? So now here you have your CH3 instead of the H, right? So CH3 is going to be known as the methyl, right? So consequently, we're going to call it so methyl. So that's going to be the first thing that is going to be kind of like attached to this oxygen instead of H, right? In the previous carboxylic acid. So methyl. So that's going to be number 1. So then we are going to use our base name from the carboxylic acid, right? So it's going to be propanoic acid. But we are going to use a different suffix, right? It's going to be not going to be like propanoic acid anymore. So it's going to be O8, right? So it's going to be that suffix, I would say. So this looks like almost propanoic acid, right? So that's the one. So that's like with an H, it's propanoic acid. But now, if we have the switch from hydrogen to methyl here, we are going to have the ester, right? By the look of that. And now we are going to name this like substituent, which is going to be methyl propanoate. So that's it. So, and then if you think backwards, right? So the person who kind of like is aware of this ester nomenclature will be like, okay, so we need to have the methyl instead of the hydrogen on the OH piece of the propanoic acid, right? So that's how it's built. So yeah, but for now, let's like try to recognize that this thing kind of like the thing in green, right? So this is going to be almost entirely the acid, right? So except H. And then this is going to be a substituent that we use to remove H and then switch it to, right? So that kind of like substitute the H, right? So that's what it is. All right, methyl propanoate. So then some more examples here, right? So here we go. So here we have the kind of like acid part, right? So this is going to be shown in what's it called in the skeletal drawing, right? So here we have the carboxylic acid with 2 carbons, technically, right? So that's all carboxylic acid up until this point, right? So then we remove hydrogen, switch it to the methyl again. So you can call it the 2-carbon carboxylic acid. It can be called either acetic acid or ethanoic acid more formally because it comes from ethane, right? So then, okay, so I'm going to go to the next page here and name it, right? So this skeletal structure on the left, in the left corner, it's going to be like this. So you can write it out and then we'll have this. Oxygen and then methyl, right? So then if I look at this part here, I'll just like in a huge circle, right? It's going to be ethanoic acid. So ethane, right? So then I have the methyl in the smaller circle. So, and then I look at this, it looks like an ester, right? Because I have the switch from the H on the OH to some kind of like alkyl chain, right? So in this case, it's going to be just the good old methyl. So methyl ethanoate, right? So that's going to be our ester. So methyl ethanoate. Methyl was used to remove the hydrogen from ethanoic acid to make O8, right? So which is going to be the sign of an ester, right? So verbally. So now maybe like more complicated case, it's going to be this guy, right? So let's redraw that in the skeletal fashion as well for just the time's sake. So it's going to be like this, right? So we have 1, 2, 3, 4. So then we'll have the carbonyl, oxygen, and then here we have our favorite aromatic ring, right? Which is going to be like that. So let's see what we have here. So we have the like acid, right? So up to the point when H was removed and switched to ethanol, apparently. We have here 1, 2, 3, 4, right? So that's going to be butane, right? So 4 carbons. So then this thing was derived from the butanoic acid, right? So let's put the root down, butane, right? So since we see that as an ester, so H was switched to the carbon kind of a chain, right? Carbon-based chain. In this case, it's going to be just a phenyl. So we will still have the what's called ester, right? O8 will be present. So now the substituent here is going to be this guy. It's going to be nothing more as than phenyl. Phenyl butanoate, right? Phenyl butanoate is the name of this compound. Okay, so and that's where we are. We will stop here and continue to the next slide on Thursday. Bye, everyone.